Hi, in this video we'll derive Maxwell's equations in terms of potentials, charges, and currents. What is more fundamental or primordial, electric and magnetic fields or potentials, charges, and currents? Maxwell equations are typically written in terms of electric field E and magnetic field B, but they can also be reduced to the form that includes scalar potential phi and vector potential A. It turns out that there are formulas for electric and magnetic fields that show that they are directly dependent on potentials and can be expressed through them. What is more fundamental, electric and magnetic fields, or the underlying potentials from which these fields actually arise? By the way, you can see in the right corner mu naught times epsilon naught, which really is 1 over c squared. We start with the conventional, well-known Maxwell's equations. Then we use the key insight that there are formulas for electric and magnetic fields. And then we'll plug these formulas for electric and magnetic fields while observing the rules of vector calculus. And by following through, we can get to these wave equations. Fields are derivatives of potentials, and this suggests that potentials might be more fundamental since they generate the fields we observe. And you'll see a term in the second equation, this one, which has a divergence of the vector potential and a time derivative of phi, scalar potential, and an indication of the speed of light. So if you will, we can make this term appear in the first equation too by just expanding it. You can see it, for instance, in this free slide from Professor Robert Harlick lecture, Generalization of Maxwell's Equations to Accommodate Scalar Fields and Longitudinal Waves. By the way, this term in parentheses, when they set it to zero, physics people call it Lorentz gauge, effectively dropping it altogether and making the equations a lot simpler. And this term is believed by some very strong and serious researchers to represent a scalar field. This term right here, the divergence of A and d phi over dt times c squared. This term appears now in both equations and represents something profound, the third type of field, the scalar field. But before we speculate or conjecture on the nature of that scalar field, let's make the equations even more compact. Let's notice that there is something going on with the potentials here, notably second spatial derivative minus second time derivative over c squared. And it turns out that there is a special operator for this kind of operation, namely D'Alembert operator. It elegantly combines second spatial derivatives with second time derivatives, while space and time are fundamentally different quantities like apples and oranges and cannot be compared or directly, but their rates of change, the first and second derivatives, can be meaningfully compared and combined because they are rates of change. So this D'Alembert operator allows us to write electromagnetic wave equations in their most compact form. So now we've hidden the complexity of the second derivatives behind the formulas, which are essentially wave expressions, except for potentials, not electromagnetic fields in this case. What we can notice now is the elegance. That first equation is scalar. It relates scalar quantities, scalar potential, to charge density, and the rate of change in time of a scalar field. Now, the second equation is all vector. It relates magnetic vector potential to current density and the gradient of the scalar field to get something vectorial from the scalar field. Now, according to the scalar field expression, this field arises from the divergence of the magnetic vector potential and the time derivative of the scalar potential phi. So this divergence of vector potential is typically not considered seriously at all. So it's considered to be arbitrary. It's set to whatever is convenient to make the math more simple. And for scalar potential to give rise to some significant scalar field, well, imagine how huge the time change should be if it is over c squared. To be anything significant, it must be comparable to c squared. So it must give something significant while being divided by c squared. So, but if you look at the divergence of A, now in typical AC, DC electrical situations, and even most RF applications, the divergence of the vector potential field is usually zero or close to zero. And you can really see that when the current flows in a closed loop, since the expression for A directly depends on current densities integrated, the A field will be purely rotational or solenoidal, it will not have any divergence. The scalar field only becomes significant under special conditions, like special geometries like toroidal coils or sharp transients, pulsed currents, voltages with very special parameters that require specific electromagnetic configurations. You can also verify that in this setup, the wave equation for scalar field will also hold, although longitudinal electroscalar waves are different in nature. The equations for them are very similar to standard transverse equations because there are quantities that change in trigonometric fashion as well. The densities, in this case, charge densities. And the solution to these second-order differential equations are indeed trigonometrical, sinusoidal for both scalar and conventional waves. So we can follow through and see that the standard wave expression will also hold in this setup. And the philosophy is that we haven't even changed anything in the original equations or proposed new equations. We just worked with established formulas and we saw how far we can get even this way, because there are enough people who propose changes to electrodynamics equations or generalizations, but we haven't gone this far yet. Hidden beneath the formulas, we can reveal the new type of field, which also obeys to the wave equations. So, the analysis reveals that electromagnetic potentials might be more fundamental than the fields themselves. Plus, a novel type of field, the scalar field, suggests itself upon revisiting the foundations of electrodynamics, indicating that there are deeper phenomena waiting to be explored. Obviously, there is a lot more that could be said on the topic and needs to be said. But until next time, bye.